let's just say we've got a loop someplace in space or wherever, or inside those Helmholtz coils, so that we can create magnetic fields here. Okay, maybe we create the magnetic field by cranking these little generators, okay? Maybe we create a reversing magnetic field by cranking this way, cranking this way, cranking this way, cranking this. We've been over the mathematics of how you figure all that out. You know, or at least you've seen the magnetic field you get from a current in a single loop, okay? If you got multiple loops, well, then you got multiples of the current you'd have in a single loop. If you got Helmholtz coils with a series of loops here and a series of loops here, you get a magnetic field in the middle that you can calculate to a good approximation using the integrals we've already worked out. Okay, we've already looked at. And should be able to do that because I might well ask to do that in the exam. Okay. So we have, anyhow, this loop. And we've got a magnetic field. That's okay. So let's just kind of sketch a set of coordinate axes so we know the direction in which we're viewing this. Okay, so this loop is kind of in the X and Z plane. And we've got a magnetic field in the Y direction. So let's just say we've got a, whatever. We've got this magnetic field. And it's more or less uniform through this whole loop. Okay. Loop radius. Hey. Magnetic field's a function of time. Fairly uniform. For any fixed, for any time you might want to specify. Well, let's just say then that V of t equals B max sine of omega t times your J vector. The unit normal to your loop. And what I mean by the loop is I mean the area increment corresponding to the loop or any area increment within the loop and area increment in the plane of the loop. And that unit normal is your J vector. So I don't really call it EMF, I was going to call it VFT, voltage around the loop, or EMF. Give me the expression for the voltage around the loop. Okay, now I'll work out for it because we got the correct expression, reasoned that out. The only hint I gave you, because people think, oh, change in flux, first flux, then change in flux. And I said, well, you want the rate of change in flux, right? Which is a change in flux per unit of time. And then very quickly got the, okay, it's the derivative of the flux with respect to time. Okay, so you get V of t. rate of change of the flux. We say this, it's B dotted with the area of the loop times the J vector. Well, the J vector here dotted with the J vector here is just going to give us 1. So it's B max sine omega t times A of the loop, the area of the loop. Of course, the area of the loop is 2 pi. Thinking we're going to need that in a minute. Thinking about the circumference. I wrote that. With the area of the loop, which is going to be pi A squared B max sine of omega t. This implies B of t is d phi dt. We're going to work out whether it's actually d phi dt or negative d phi dt. And the derivative is straightforward. We get a factor of omega, and then we get a cosine function. So we put all that together, and this is very easy to derive, okay? Now again, I don't want to worry too much about the plus and minus in this. We'll fix it if we need a minus. And we'll work that out by the right-hand rule. So my question then is, what's the electric field around this loop? So now, pose this question. What's the magnitude of V around the loop? Okay, again, got some good reason there. I didn't have to give any hints. The electric field around the loop, well, the potential difference around the loop, but I'm going to kind of gloss over the symmetry argument, but the symmetry is pretty obvious here. I'll say by the symmetry and the assumed uniformity of B, within the loop, your voltage is your electric field times your circumference. You got to work out directions and all that to be sure. You got to visualize it. Okay. but the electric field is, well, I'm not going to go through the whole argument. V is your electric field times circumference, which is exactly what you said. Again, we want to take that whole argument back to the definition of potential difference and so forth. Circumference is, of course, 2 pi times the radius. The electric field is a function of t. It's then pi a squared omega v max over 2 pi a times your cosine of omega t, which didn't have a lot of room to write, but then you got a pi here that divides this pi, you got an a that divides the a squared. So you end up with a somewhat simpler expression, okay? Now, the only thing is it took a little longer to get all that. I hope, although it didn't take all that long, which was done well. Your voltage is actually your EMF, and you really use EMF of T instead of V of T, if you want to write it, because you kind of think of, you generally use this when you have an induced magnetic field, okay? And EMF due to some kind of induction, okay? Should be a negative here, which of course then is negative here and negative here, negative in every step. And you can work out in terms of orientation. Go back to the most basic relationships, okay, which is that your charge relates this way to your magnetic field, moving charge, QV cross B, okay? And the field you get, okay, is that thing with the R vector, okay? Like your QV cross your R vector, divided by the R squared, multiplied by the unit vector and all that stuff, okay? Those are the two rules. Easy to write out, not that hard to remember. Second one's a little harder. And you use those rules to just analyze what's going on in here. Let's consider an electron here, okay? Or charge, just a charge Q somewhere in here that's allowed to move. What's going to happen as a result of this changing magnetic field, okay? And then figure out why you've got a minus. Of course, figure out why the whole thing works. Then you'll have a good understanding. Okay, so anyhow, you've got E of T, and you're going to have a negative on this. The other thing about the negative is there's still questions about orientation and stuff, so it's not all that important. At least you understand there's an electric field here. I mean, it is important to get these orientations right and everything, but the bottom line is you have an electric field as a result of your changing magnetic field. And it's a changing electric field. As a magnetic field changes, the electric field changes. Okay? In fact, the reason you can see me and I can see you is that number one, we've got functional eyes that respond to electromagnetic radiation, okay? Electromagnetic radiation is the radiation here. Well, our eyes are adapted to the visible range, which is why we built visible fluorescence, okay? Fluorescence that produce light in the visible, in the visible range. Most of the energy comes off the sun, is in the visible range, okay? No coincidence, okay, that our eyes have adapted to the radiation from the sun. Well, the whole thing is now this electromagnetic radiation is nothing but a series of propagating oscillatory behavior between a magnetic field in one direction and an electric field in the other direction, okay? And we'll kind of put them in this direction. Your magnetic field changes, causing your electric field to change, which causes your magnetic field to change. They kind of oscillate like this and propagate in this direction. That's light. That's any electromagnetic radiation. We're not going to be able to get into the details of that because we're just not going to have time. And it's unfortunate because I'd really like to get into it. But on the other hand, to actually solve Maxwell's equations and get all this requires a little bit more mathematics than we can assume in this course. So we have to kind of wave our hands over some of it. Now, you know enough multivariable calculus, you could do it. But it's beyond the scope of the university physics course. Let me get into in a more advanced course. If you're looking at propagation of electromagnetic radiation and fiber optic cables, if you're an electrical engineer, you might get into that. And you're going to need a little more mathematics, but you have everything you're going to need to build that, if your multivariable calculus is up to it. And you need a little differential equations too. The multivariable calculus is a big deal. Okay, well, anyhow, there we have it. So now we got this electric field, and we know that this electric field isn't just confined to this loop. Whether this loop is there or not, the electric field is there. Okay, so you have an electric field within these coils. And if you happen to put a loop of conducting wire into it, you'll get a current flowing. If you put a loop of non-conducting PVC or something, electric field's still there, but the PVC isn't going to allow charges to migrate and give you any significant current. Now the question is, then, actually, there is a question. So I'm going to think about before we go too much further. But okay, we'll stick with this. You got an electric field in there. That's what we want to understand so that we can go on with what we're going to do in lab and so forth. Okay. Another thing, we want to talk about solenoids. Okay. Now we want to talk about a solenoid that has a length L with N loops, radius A. And it's kind of like this. It's just a bunch of coils that are spread out over some distance. Okay, now if you take this thing, it's a little ragged, but you can see you can see kind of a bunch of loops spread out over this distance. Now, they're not all at distance A from the axis because, you know, you have loops on top of loops and stuff like that, but you get the idea. Okay, so, and an actual solenoid has a lot of those characteristics. It's not perfect, but you want to make it as good as you can. So, and you make it better than I drew it. That loop's too small compared to that one, but you get the idea. A bunch of loops spread out over some length, and it's uniformly spread out and everything's homogeneous, okay? Now, before we can talk about the magnetic field of this, we've got to be sure we've got Ampere's law, okay? Which we didn't really talk a lot about, but it's implicit, it's in the chapter and so forth. But let's make sure we understand what it's saying. Remember, we developed the magnetic field for long straight wire by doing an integral, okay? Just using the relationship between the magnetic field at a point and the current in a segment at some angle. You got your R vector, and you do your cross product of your I delta L with R and all that stuff, okay? You end up in this situation with a magnetic field. It really looks like I drew that magnetic field in the wrong direction. So I was looking at the loop the wrong way. Anyhow, the magnetic field surrounds the wire. If the current's in this direction, use your right-hand rule and you see the way the magnetic field surrounds it. I think these little arrows here are all wrong. Actually, this one's right, and then I drew the rest of them wrong. Okay, but there's kind of a picture. It has the little arrows in the right direction and the big arrow here. Okay, so the point is, we should understand this pretty well, and I think we do. Your magnetic field times its circumference turns out to be 4 pi k prime I, or mu naught I. Then for any loop enclosing your current, if you do a line integral of your magnetic field dotted with your displacement increment, okay? Then, of course, for the circular loop centered at the wire, you just multiply the magnetic field times the circumference, but this generalizes it to the line integral of the magnetic field around any path. Component of the magnetic field tangent to the path, okay? Multiplied by the length of the path increment, which can be thought of as kind of an average of your magnetic field times the length of your loop. Just using the general idea of an integral as an average value times the interval of integration. You get this result here, okay? Which is just like this. This I is enclosed within this circle, so I didn't write the enclosed, but this is Ampere's law, okay? So for any path enclosing I, you have this. Now let's go back to the solenoid and see how that applies. Let's just take a, just a picture. Short solenoid here. And let's say we've got the current flowing in, well, current goes in here. And I guess the way I've drawn it, current maybe goes around in this direction. So maybe the direction of the current is like so. This is not a very good picture. The point is, you can draw a path through these loops. So let's just say a couple of loops. Okay, so you got a path that comes down here, passes through the loops. I just don't like my picture much, but do you get the idea? Does this make sense? It's like you have this thing and you make a path that, let's say, goes right down through here, down to the center. And then it goes over a little ways, and then comes back up and comes around like this. Because of time, I'm not going to go into too much detail about this, except to say that out here, the magnetic fields that you get from the different segments here pretty much amount to nothing, okay? Along these paths, well, the magnetic fields of these things reinforce each other. So magnetic fields in this direction within the loop, okay? Doesn't amount to much out here, and if it does, just make the loop a lot bigger. Make this a lot further from the loop than I drew it, okay? If you think you got some significant effect of these magnetic, of the magnetic field, although if you work it out with all the directions and stuff like that, it turns out it doesn't have to be all that far away, okay? The basic idea, though, is that around this loop, you've got magnetic fields, okay, within the loop. Let's just say that this represents the outer surface of the solenoid, okay, the outer surface of all these loops. Then you're going to have a magnetic field. Now, if your current's going this way and looping around that way, your magnetic field might actually be in this direction, okay, if the current is going around this way. And that current reinforces itself everywhere within this loop to be pretty uniform in a way similar to what I described for the Helmholtz coils, okay? So this is kind of almost like a set of Helmholtz coils with some real attitude, okay? They don't have much room in here, and the Helmholtz coils give you some room to put things in with a uniform magnetic field, but you have a magnetic field that's nearly uniform. In a direction parallel to the axis. And I should say within the solenoid. And so outside the solenoid, the magnetic field is pretty much non-existent, okay? So that now if you do your path integral, okay, so let's say you do a path integral in this direction. Up here, your magnetic field is 0, so B dot delta L for any delta L is pretty much 0. On these two segments, B is perpendicular to delta L, so B dot delta L is 0. So in the ideal case, B dot delta L up here is 0 for any segment. For any segment here or here, B is perpendicular to delta L, so B dot delta L is 0. And here, the magnitude of your B dot delta L is just B delta L. Along any segment here. Since, and I don't have room to write it, but there's a sense B and delta L are both along the axis of the solenoid. Okay, so they're parallel. They might be in opposite directions, which is why I have absolute value signs around it, but it's just this. Okay. Well, it implies that then a total path interval is first of all mu naught times I enclosed. And that's equal to B times delta X. Now what's delta X? I didn't put any dimensions in the loop, but now this distance here is going to be your delta X. So now let's do a slightly better picture of your solenoid. Here's your solenoid. I'm not going to draw all the loops, but you understand this is just a bunch of loops within this envelope here, okay? Here's a path that penetrates down to some point within the solenoid where the magnetic field is constant. So same picture that we have here applies here. Again, we have delta X up here. Doesn't matter what this length is because the contributions here to the integral of your magnetic field around the path are zero because your magnetic field is either zero out here or perpendicular to the path in here. Magnetic field is parallel to the path down here. So the integral around the path, we'll call this path C, closed integral around the path C. So B dot DL, where DL, delta L's just all your little segments. You get, let me divide this path into a million segments. That's about a million. Okay. Just invoke that picture. Your integral B dot delta L is then equal to, or at least the magnitude of your integral is equal to B delta X. But that's also equal to mu naught times I enclosed. Okay, again, it's the same solenoid. I'll remind you here, length L, N loops. Radius A. Well, what's your I enclosed? How much current do you enclose in distance delta x? Well, just told me it's delta x over L times M, because N over L is the number you have per unit of length, right? You got N of them per unit of length. There are many ways to look at this. You set up proportionality, right? But if you got N per unit length, then you multiply by the length, which is delta x, the length of the segment here, okay? And this is, of course, okay, this is how many loops have a current going through the path C, cutting inside the path C. So be this times current, okay? This many loops multiplied by the current. So what's B? Okay, now there really was a discrepancy between the formula the book had and what I had because, well, it comes down to the fact I said there are N loops in the whole solenoid, and your book used a different assumption. If you take what we got here, we see that we get mu naught I times the number of loops per unit length. Your text gets mu naught I times M. No L involved. Why? Well, I told you to look it up, and your penalty for not watching the video first is you're going to have to look it up. And hopefully you'll then see that the text says that N is the number of loops, which is what I said, but then your text says per unit length. No, I just went ahead and derived it on the assumption that N is your number of loops, which makes perfect sense to me. Okay, because I don't do a whole lot with solenoids except in the lab here once a year. And I know how to derive this, okay? So I can make my own assumptions. And if the book wants to make their own assumptions, that's okay. Mine are better than theirs, obviously, but theirs are probably more in tune with the way engineers do it. And probably with the way physicists do it. Physicists actually can't do a lot of stuff with solenoids. So they're all wrong, I'm right, but you can make your own choice who's right and who's wrong. They're consistent, totally consistent if N is the number of loops per unit length, I say that N is the number of loops and L is the length, so N over L is the number of loops per unit length. Well, totally consistent. I probably ought to go with the book's notation, but I think it's inherently confusing to use N for the number of loops per unit length, because mathematically usually N is your total number of things. So there may be a little confusion there. You reconcile it and understand that in the standard notation, I suppose, N is the number of loops per unit length, not the total number of loops. And also, I said, you know, you need to look at the circular solenoid. Okay, this reinforces multivariable calculus, which everybody's had, and we don't really use here, but you want to keep reinforcing it because it's so important if you go into especially electrical engineering. With that, I'll close, except to say you really need to look at that toroidal solenoid too. The derivation is very similar, but there's some slight differences in the results. Actually, I'm not going to quite stop there because I will say that when the book does a toroidal solenoid, they use a capital N instead of a little n, and capital N is the total number of loops. So I find that inconsistent and inherently distracting and confusing unless you use it a lot. But you're going to have to deal with it. You're going to have to understand what little n and big N means. So take another look at the toroidal solenoid. Derivation is very similar to this one, but the geometry is just a little different, and it's going to be good for you to see it.